Okay, in this video we'll be visualizing the derivative of sine theta just for the fun of it, but also to showcase the usefulness of some of the visual work and understanding we've built so far. So the question is quite simple. If y equals sine theta, then what is the derivative? What's the gradient of the sine function or the sine wave for any x value we want? So of course we'll be setting this up not on the graph directly, but on a unit circle. But just a heads up, for this to work, we need to actually measure angles not in degrees, but in radians. Now, you may or may not have met radians before, but the idea is that rather than use an arbitrary measure like degrees, we measure angle by measuring a physical distance, a length, around the unit circle. So if we have an angle going all the way around, the circumference of the unit circle is of course 2 pi. So we're going to say the angle is also 2 pi rather than 360 degrees, which is what we're used to. And so for example, instead of 180 degrees for the straight angle, we just say it's pi, because that's exactly how far we've physically moved around the unit circle. A right angle would be pi on 2, and so on. And if you haven't met these before, you might be wondering, well, why not just use degrees? Why not stick with what's easy? Well, the reason is because we're trying to differentiate a trig function, meaning we're trying to measure how the trig function responds to a small change in the angle. And so because the sine function is measuring a physical length on the unit circle, which is just the vertical height of the point, right? Yeah, down is negative, but it's still sort of like a length with a positive and negative direction. The point is, if we're going to compare a change in length with a change in angle, a fair comparison can only be made if these two things are operating under the same scale. And the best way to do that is to do what we just did with radians, to measure angle precisely by measuring length. Okay, so that was a bit of a tangent, but the point is this length here is theta, just as much as the angle here is theta. So to differentiate, we think about pushing the angle theta slightly across, which does this, and we're trying to measure dy, the resulting change in the y value, which will be this tiny vertical length here. Okay, because sine measures y values, remember. Now, coming in a bit closer, remember that the angle we have pushed theta across by is exactly the length of this arc, which is why the whole radians thing was so crucial. But really, as we limit these distances to 0, it's almost like this arc isn't even an arc anymore. It's approaching more or less a straight line. So we could even complete the right angle triangle looking thing here, and that gives us a lot of information about the relationship between dy and d theta, which was what we were after in the first place. Now, from the first basic right angle triangle we set up, we can actually see that this angle in here is 90 degrees minus theta. Yeah, we're meant to be in radians, but for now we're back in the world of right angle trig, so just makes things easier here, right? So it would be hard to fit this label in the original picture, so you may need to rewind the video, see the construction of the first right angle triangle in this picture, and convince yourself that this angle is indeed 90 degrees minus theta. But that shouldn't be too difficult a job for you. And now remember, in the limit, we are saying that this tiny d theta arc here is essentially a straight line, and it would be the same going the other way as well. Then, because of the symmetry of a circle about its own radius, we have a right angle in here as well. And so by completing a straight angle along the vertical here, we find that this angle in the orange triangle must be exactly theta itself. And that is enough to establish the relationship between dy and d theta in the orange right angle triangle. Relative to the angle theta, dy acts as the so-called adjacent. D theta is of course the hypotenuse, meaning dy d theta is just cosine theta, And we're done, okay? That's the derivative of the sine function, okay? Before we finish though, I want to have a look at how this plays out on a graph, okay? This fact that the derivative of sine is cosine, that should have some visual implications on the graph of sine x as well. So here's a graph. It bounces like that forever, so even if we knew nothing, we'd expect any kind of gradient graph to follow suit and be periodic, to bounce around forever as well, okay? Now, as we've seen before, the graph is flat at extreme ends here, so at the top of the hill or the bottom of the valley, the graph is flat, and so the gradient there must be 0. Then at the start of the sine curve, or where x equals 0, this is actually the steepest we're ever going to get. Okay, once the curve gets started, it immediately starts to shallow out towards the top of that first hill. So we expect the gradient to be at a maximum positive here. And we're going to fly past that flat point to this point here where it's the steepest downhill we're going to get. And that's how it's going to bounce back and forth forever. So it makes sense that this gradient function fits the shape of the cosine graph, and the work we did before confirms that it is indeed exactly the cosine graph, not just in shape, but also in value as well, and that's pretty cool. Okay, so that's all for this one. Thanks for watching. See you around.